it's all running in the CPU. It's whether you have this another layer of sort of goo in there.
Yeah, I mean, I'll add to that in the sense that if you talk about an abstract machine, one of the things you get with that in managed runtime is you get a definition of semantics of that machine that is just easier to deal with. I mean, and the associated type system in the common language runtime, you have a type system that has defined semantics. You've got all the data that sits around to support that type system at runtime. And so it gives you an abstraction that you can reason about more effectively, I think. I think if you cut it at a lower level layer, you really don't have any well-defined semantics for the things that you could then apply tools to and reason about. So I would make that distinction.
Yeah, I guess so. At one time, Sun was going to build a chip that ran Java bytecodes or something like that. Is that, what is that?
Well-defined, machine instruction set architectures, commercial machine instruction set architectures tend to be pretty damn well-defined.
Well,
I have much less argument with
Should we postpone any further discussion?
Yeah. Okay, so thinking about all these virtual machines, there's sort of two things that basically are in common, all of them. One of which is they all seem to be the target of either a programmer or a compiler. So like this one sort of attribute of them is that something's writing code for it. So for example, the low-level virtual machines, you basically had someone build something for the hardware that ran on it. For Java, you get like a Java compiler or something like that. That actually generates stuff. Generally, you have someone building the code. And the other thing is, they're all just a level of indirection, effectively. And this old saying in computer science that you can solve any problem is that it's the same game everybody plays. You put a level there. It costs you something, since now you have this level to go through. But then you say, look at all the neat things I can do with it. I can isolate it from other programs, or I can do this or that. And that benefits you way more than any little cost of the level that I put in there. And so this sort of, I view all these virtual machines as basically an idea of a level of indirection. So if you look at all these virtual machines, there's like a bunch of attributes I pulled out. Compatibility, I'll go over these in more detail. Isolation, encapsulation, and performance. And so, I'm going to move faster. Just the idea of a virtual machine is a specification. And the specification is that if you write software for that specification, it should run. And so, here, if you view this thing as sort of making cuts at different levels, the sort of lower level VMs basically run all the software that was targeted for that hardware. If you go to a para-virtualization approach, you're limited to all applications that are run on the OS you ported for that approach. If you're on an OS level 1, you're only you can run any of the applications that are built for that OS. And then if you have a high-level language VM, you effectively run all any program that's capable of being expressed in the bytecode for that. So from a compatibility point of view, you said again, it's a restricted subset, so it's software compatibility. So one of the things that people had forgotten about virtual machine monitors, this low-level type, is that they provide, if you can really build the virtual machine so it matches the hardware, you get basically all the software for free. When we started VMware, we built something that looked enough like an x86 at a PC that it ran all the operating systems that run on this thing. And people would ask, can this thing run Oracle? And I go, well, the complexity we have is to match the x86 hardware, not the complexity of this particular software on it. So it runs anything, regardless of how many millions of lines. So this gives you actually, from a point of view of if your goal is software compatibility, it gives you the most compatible, most sort of compatibility there. It's really comparing the hardware for the PC hasn't changed that dramatically over the years. It has the performance and stuff, but the interface. One of the things that's truly amazing about this is you can probably take DOS 1.0 and run it on it. It's like it's a pretty amazing story of backward compatibility. So, OS APIs are like really complex and always changing. I think we were talking about lobby earlier. That's an example of something that basically, Sun was just sort of Microsoft sort of laughing at that approach, since we could change this thing faster and we could even catch up to it, and so effectively what ended up happening is you have something with 80,000 calls and adding, you can't really track that. The other sort of claim VMs have is that if you have something in one virtual machine, you should not be able to get out of that sandbox and attack other virtual machines or the virtualization layer. This is an isolation property. And so basically the VMs effectively, as a process of that, since they contain the software, they can basically look at all the requests to get out of the sandbox and decide whether they want to approve them or not. You can have some kind of policy that describes what kind of communication comes out of the sandbox. And so here, this isolation property, the kind of assurance you get really depends on the implementation. And what this is boiled down into and sort of practice is the sort of the complexity or size of the interface. And so one of the things that's been true about the hardware interface about hardware level virtual machine compared to something higher like the Win32 system call, it's a lot smaller, and effectively what you can do is get something that you have some confidence that you can have like strong isolation in it. So this is certainly true in the 60s when IBM, and it's pretty much true today, is that when you write one of these low-level virtual machine monitors, you have something that tries to configure the hardware to actually do the isolation. You set it up the memory map units of the virtual machine so they cannot touch somebody else's page. And the hope was that they validated the processor enough that someone can't crack out of that hardware sandbox. And hopefully the size of your code is small enough and you have some confidence that they can't somehow figure out how to trick it to let you out of that sandbox. So these low-level VMs have a good history of providing really high assurance isolation. There should be no way of sort of getting out of this thing. This is should be able to handle both accidents and malicious code. This is not true of most OSs these days. Another thing you can do is once you have something running in a virtual machine is you can encapsulate it. And this once you got the software there, you can do things like save its execution, say transport it over networks, control all the input and output to it. So basically, you can now treat this whole virtual machine as something like you can manage, on a group of servers, for example, while it's running, move it between sort of boxes and stuff like that. And people do that with Java and application servers and virtual machines, and you can also do that with VMware's products if you run a whole Windows or Linux environments. It's the same sort of property, encapsulating the software. It also allows you to sort of decouple the software from the hardware. It turns out that, I'll talk about a little bit more about this later, but basically this idea of sort of having your software tightly coupled with the hardware turns to all kinds of system administration problems. It really allows you to treat the VM as a first-class object. So go quickly here. The final thing is about performance overheads, and I notice there's a lot of performance talk about Java and stuff like that. It's the same is true for hardware level virtual machines. The trick that was developed for the 60s was that if you want to emulate a CPU and you happen to be running on a CPU of that same type and you can use it directly, you can get something that runs with almost no slowdown. It's a similar thing if you wanted to emulate physical memory using sort of the memory of the machine and a disk with a disk. And so the tricks that are used in the 60s are largely also used today in virtual machines, where you configure the hardware in such a way you can just give it to the virtual machine in a safe way.
Don't you have a disadvantage over IBM where they can define the instruction set and really know what was privileged and what wasn't?
Right. That's why there's kind of only one VMware. It was lots of competition. It turned out to be a remarkably hard problem to do. So here's an interesting thing: is that there's this theory that if you have multiple levels of indirection, you only really need one level of indirection to solve any problem. Multiple levels of it is sort of gratuitous, since you know, like a theory. So your thought would be somebody's going to come up with a single sort of level here, and everybody will go to it. And I think this will actually not happen. And the reason it won't happen is the benefits you get from high-level language virtual machines is managed runtime, and the benefits you get from these low-level ones are fairly distinct. You know, and the high-level one